Welcome back to NANDGAME, and today we are going to start the memory section. Last time we built the ALU, which takes A and B inputs, those are just like numbers, and control bits, which lets the ALU know what kind of operation we want it to perform, and then outputs a result. But it would be really annoying if every time we want to do an operation, we have to manually input A, manually input B, manually input our control bits, and then save our output by, I don't know, writing it down in a notebook or something. Ultimately, we want to have some automatic memory where we can save our outputs, store our inputs, and even have some information about what kind of program we want to run. So that is what we are building here today. So let's get started with level 1, our SR latch. Okay, so an SR latch or set reset latch is a component that can hold a single bit output. When S equals 1, that sets the output to 1. When R equals 1, that sets the output to 0. The key here is that when both S and R are 1, the output is unchanged. It will just output whatever the previous value was. And then when it's at 0, 0, like as it is right now, it's undefined. So I think the obvious way to start would be to take an and we can try doing what we've done before, where we look at where the output is 1 and just focus on that. So we have S and not R. And this sort of gets what we want, at least the start of it. When S is 1 and R is 0, output 1. When S is 0 and R is 1, we output 0. But obviously, this is where our problem lies. Because if we have things in this state, where S is 1 and R is 0, we should be able to change this to 1 and 1, and the output shouldn't change. But it does. So let's get rid of this right now. To solve this problem, you need a different tool. You need something called circular dependency, which we haven't used up until now. So just as an example, let's use an OR gate here, hook that up to the output, and just hook up A to S here. Circular dependency is when we take the B value and hook it up to its own output. And I think what happens here doesn't seem like a big deal, but it has pretty big implications. So when we start, both A and B are 0, and the output is 0. But as soon as we turn this to 1, well then it outputs 1, and it feeds back so the B value becomes 1 as well. And now no matter what we do, we can keep turning this on and off, well it stays as 1. We flip the switch once, and now no matter what we do here, we've permanently changed the state. In previous problems we've created circuits, and we've always been able to tell what the output is based on our inputs. But here we now have to think in a different dimension, because our outputs don't just depend on the inputs, but it depends on the previous state. If I tell you the input to this circuit is 0, I can't necessarily tell you what the output is going to be until I know what the previous state was. If the previous state was 0, it's going to be 0. If the previous state was 1, then it's going to be 1. Hopefully this simple example makes sense. We've created a circuit that, in a way, kind of remembers the previous state. This really isn't that interesting because we can set the state once, and once we set it, we can't really do anything. So we're going to go back to basics here and go to our NAND. And we've set the NAND gate up in a similar way. And you can see as long as S is 0, we're kind of in this steady state here, because 0 and 1 output 1, and that's just feeding back to the same state. But as soon as I turn this S to 1, what's going to happen? The A and B inputs will both be 1, which will turn the output to 0, but then that'll feed back into the B output, which will cause the output to be 1 again, which will feed back into the B output, which will cause both of them to be 1, which will cause the output to be 0, and so on and so forth. So what happens? I guess let's just try it. Well, we kind of create a logical error. Here it says the component did not reach a stable state. The output is oscillating between 1 and 0, exactly as we described. So this is the sort of thing we're trying to avoid here. And that's okay, because we have 2 inputs anyway. And let's just take another NAND and feed it in there. And instead of feeding this NAND into itself, let's try feeding it opposite. Now immediately see if S is 1 and R is 0, the NAND gate on the right has 0, 0 as input, which creates 1 as an output, feeds into the NAND on the left, making them both 1, and that outputs 0. And we see we get the opposite occurring when we have 0, 1. That is, of course, opposite what we want here. We want S1, R0 to output 1, and S0, R1 to output 0. So let's just try switching that. And now you can see that that does seem to work. 0, 1, output 0. 1, 0, outputs 1. But we've so far not shown that this is any better than just using the AND and the inverter that we started with. But if you follow the logic, you'll see something interesting happens when we flip this R to 1 so that they're both 1. Nothing happens to the output. Why? Well, the NAND on the right is getting 0 and 1 as inputs, which causes a 1 output for the NAND. That 1 output feeds into the left one, which is now 1 and 1, which outputs 0. So we haven't changed anything. Our output remains 1. But if we set the output to 0, and then we go back to 1, 1, well, it stays 0 for the exact opposite reason. The logic is exactly the same, just mirrored. If this is hard to think about, I don't think you're alone. It's really hard for me to think about too. And I do think it's one of those things that you just have to sit and look at and play with the logic in order for it to make sense. But this should be the basic solution. Let's check it out. Yep, 2 components used, 2 NAND gates. This is optimal. D-latch. Now a D-latch is similar to the SR latch, but it works a little bit different. Basically, if ST, which stands for store, is set to 1, then we're going to output whatever the D value is, the data value. So store 1 and data 0, you're outputting 0. If store is 1 and data is 1, you're outputting 1. If store is off, you should be able to flip this data switch on and off as much as you want. It shouldn't change the output at all. You can only change the value of the output by turning store on. So how do we do this? Well, a D-latch is really an extension of our SR latch. And we do have our SR latch component here, but I think it'll make more sense to hook it up as we did before. But instead of just stopping here, we are creating this complicated monstrosity. So I'm not really sure how you get to this solution without knowing about it previously. I feel like this is something you learn about first, rather than kind of stumbling into the solution. But if, again, you go through the logical steps, it makes sense. If ST is set to 0, well, you can see doing anything with this D, the data, is doing nothing. Why? Because the only way to change these 2 NAND gates right here is to have both inputs be 1. But since our store is hooked up to both of them and our store is set to 0, changing this D won't do anything to our final output. But when ST is 1, well, now we can actually activate these NAND gates. Switch D to 1, and you can, again, see what happens. The NAND on the lower right here turns to 0, which goes into the B on the NAND of the upper right. And with this inverter here, the NAND on the lower left is 1, causing both the upper left's inputs to be 1, causing its output to be 0, and turning the upper right NAND on, so it outputs 1, and then the opposite logic essentially occurs for 0. We set it to 1, turn ST off. Again, same as before, we're not changing these values of the lower NANDs, so nothing is changing, no matter how much we try to change this data value. Confusing? Yes, I think anything with a circular dependency gets confusing. The nice thing about this game is that it really does let you play with the logic and see what's happening. And like last time, this is the basic setup for the D-latch, so we should check solution, and this should be optimal. Yep. And lucky for us, we only have to make these components once, and when we go to actually building out our registers and our memory, we just kind of have to hook these parts up together. It becomes a lot less complicated with these things already built. Data flip-flop. DFF component stores and outputs 1 bit. The output does not update immediately when the input changes. Changes happen in phases timed by the clock. This is a lot of words here, and I think it makes it seem more complicated than it actually is. The general idea of the clock is that in the real world, our components are actually electronic things. And electricity doesn't flow immediately, or it'll just take a little bit more time for electricity to propagate through some circuits as opposed to other circuits, depending on its complexity. And we really want everything to happen in sync. So we'll have a clock, which will just turn on and off in sequence, and we only want things to happen to the beat of this drum. So our data flip-flop here just ensures that our data outputs happen at that sort of predictable time interval. So you can see these references here to store and data flags, which should make it immediately obvious that we're going to be dealing with a data latch of some kind. And let's just run through each of these instructions one at a time. When CL equals 0, store and data can change in this stage. Okay, that doesn't really tell us much, so we're just going to move along to this one. If store is 1, when the clock changes to 1, the current value of D is stored, but the stored value is not yet output. So we'll hook up our data, and what we want is only to store the data when the clock is 1 and when store is 1. So we'll just use an AND here and hook up store and the clock to that. And that'll be hooked up to our store latch, so that the value in this data latch will only change if both store and clock are 1. So it's changing now because both of those are 1, and if either one is off, it won't change. Or if both of them are off, it won't change. It'll just stay the same in our data latch. Our data latch will keep outputting the same thing. Okay, so that's done. Finally, when the clock changes to 0, the previously stored value is output. So we only want to output the value that's in this latch when the clock changes from 1 to 0. And the easiest way to do it, at least the easiest way I can think of, is just to add another data latch. We're going to funnel the data from the previous latch, and instead of it outputting when clock is 1, well, we want it to actually only output when the clock is 0, so we need to invert this, and then we should just be able to hook that right up. So if store is 0 and the clock is 0, then we can change our data and nothing happens to our output. If store is 1 and clock is 1, we can change our value on this first data latch, and then when we change the value on the clock to 0, that should turn on the store for this upper data latch, which should then output our 0. And that's what happens. Check that solution. 4 components used, 13 NAND gates total, and this is the optimal solution. Another way to think of it is that we're kind of keeping our data on deck in this first latch, and then using this second latch to output the data only when we want it to be outputted, which is when the clock turns from 1 to 0. Okay, next level. Register. So we can use our data flip-flop to store a single bit of data, but here we want to be able to store 2 bits of data. And so this is called a register. And typically you're going to have registers that are more than just 2 bits. For this, we're going to need a 16-bit register, but it looks like we'll just get that once we solve this level. And really, a 2-bit register will just be hooking together 2 data flip-flops. So for both of them, we'll hook up store to store and clock to clock. So we'll take this one on the left, hook up the data to D1 and the output to the D1 output. And then same thing with the one on the right, we'll hook up the data to the D0 input and hook up the output to the D0 output. And that's all this is really. It's just 2 data flip-flops that happen to be hooked up to the same store signal and the same clock signal. Check solution, 2 components used. This is the simplest possible solution. And again, if you wanted a bigger register, you would just keep adding data flip-flops, as many as you needed. So let's move on. The next task is to build a counter which increments the number at each clock cycle. Counters are a core component in a processor because they drive the execution of instructions. All right, let's just start by creating a register whose value will increment every clock cycle, and we'll worry about this store and X value after that. Let's hook that up to our output, and then we have our increment component. For now, let's hook it up directly to our X input. That's the number input that's going into the register. And what do we want to increment? Well, we want to increment the number that's already in the register. So we'll just pass that around, kind of pin it over here to make it look a little bit neater. Let's hook up our clock and let's hook up store. And remember, store has to be on in order to take in values. And now every time the clock goes from 1 to 0, we should see this register increment. And there you go. Looks like it is going up by 1 for every time it goes from 1 to 0. But we kind of want this store on regardless of what we're doing. So we're just going to hook that straight up to a NAND gate, which always outputs 1 as long as nothing is hooked up to it. And there we go. Our incrementer works. And then our store really here is an override. What we want is to pass in this X value if the store is 1 and pass in the incremented value if the store is 0. So we can choose a selector for that. We'll hook up select to the store input. If store is 1, we want to input X. And we'll have to move this because if store is 0, we want to input the incremented value. And then pass that selector to X. And there we go. If our store is 0, then this clock should just continue to increment. Yep, you can see it 26, 27, 28. Now let's check if our override works. We can change our input value X here to 100. And when we set the store input to 1, as soon as we change this clock to 0, it should overwrite this 21 value with our 100. And yep, there we go. We turn that off again, and we just keep incrementing from there. All right, this should work. Let's try it. All right, perfect. And again, simplest possible solution. We're on a roll. Okay, so I think this is the last level. We're going to create our RAM. And it basically tells you what we're doing right here. We have these registers, and we can get more memory just by stacking these registers. And ultimately, we're going to be able to need to pick and choose which registers we're reading and writing to. So we have this AD as an address. It looks like here we only need two 16-bit registers. So we only have a 1-bit address, which is fine. All right, we know we need 2 registers. So let's just get these on the board right away. Hook up the clocks. And based on the address, we want to be able to route this X value. Let's just set it to 100 just so we can see something. We want to route this X value to either the register on the left or the register on the right. So in order to turn on the ability to write, we have to set this ST to 1. And whether we want to write is going to be based on the ST input here. So if it's 1, that means we want to write. And we want to turn the store on to whichever register we want to write over. And the switch is going to be the address. So if address is 0, then this C0 output will be 1, assuming the store is on. And we'll hook up that C0 to the register on the right, hook up C1 to the register on the left, and we'll call this register 0 on the right and register 1 on the left. And now by changing the address, we can change which register we write to. And since we're only turning on the store value for the address that's selected, we can hook up the X directly into both these registers. So I've set this to 100 with store on, and we are addressing register 0. So we can do a clock cycle, and that turns that one to 100. And our register 1, our register on the left here, doesn't change at all. And maybe we want to change register 1 to 20, let's say. We just change the address, change our X input value, and then just cycle the clock once. And our register 1 has a value of 20, and our register 0 still has a value of 100. All right, so we've got the write function working properly. Now we just have to output the correct address. And luckily we have our pre-built select component here. And the S input, the switch, is going to hook up again to our address. We'll hook up D1 to what we're calling register 1 and D0 to register 0, hook up that to the output, and you can see it's outputting whichever register we are addressing. Register 0 is outputting 100, and register 1, when we switch the address, is outputting 20. And that's it. We're really just routing data here. Check solution, and we once again got the simplest possible solution. And it mentions here again that we're just using 2 16-bit registers, but you really just repeat this whole process with 3, 4, 5, 6, 7, however many registers you want. It's the same setup. And that's it for memory. I had mentioned in the beginning that memory is tricky, but really it's these basic components, right? The SR latch, the D latch. Those are concepts which get tricky. And then after that, we're just using those components to build more complex things, really just repeating patterns over and over again. So hopefully you felt that way too, that these first 2 were a little bit tough and then it just got easier from there. And I'm hoping that we see the same thing for the processor, which is next up. That now that we've built all these fundamental components, this final section should be hopefully pretty easy, but we'll find out next time. Thanks again for watching.